this is Jyoti Sharma once again in front of you, discussing the Aktu University question paper solution for the year 23-24 even semester of the subject Fundamentals of Electrical Engineering, having a subject code of BEE 101 under Aktu. So in the previous two lectures, we have seen section A, which is having 7 short questions. We have seen section B, which is having question number 2, having 5 parts, 7 marks each. Now moving on with the section C, which is having 5 questions, but each question is having two questions, A and B part, and the student is suggested to have one question being opted, but the solution would be discussed for all the parts. Fine. So the third question, having the first part as find the current in 4 ohms resistance in the figure using mesh analysis. Fine. So for the circuit which is being shown, we need to find the current in 4 ohms in this resistance using mesh analysis. Now in mesh analysis, what is the very first step? We used to go with the number of meshes. How many number of meshes can be formed in this, if at all I see? There's 1, 2 and 3. So let's give the name of the meshes. So say this is mesh 1 with the name I1, this is mesh 2 I2, this is mesh 3 I3. Right? So the 3 mesh currents, all I have taken clockwise. The direction can be assumed in our own direction. One can be clockwise, one can be anti-clockwise. The directions can be assumed. So if at all I see in this, the last mesh I3, that itself is having a current source at the corner. So I may be assuming that I3 is equals to, just see with the symbol, we are going for the clockwise direction, but the current which is there in this current source, that is upward in the clockwise, anti-clockwise direction. So we can be saying that I3 is equals to minus 2 amperes. So we already know one of the mesh current, which is minus 2 ampere, right? That means if at all we know the value, want to know the value of the other 2 mesh currents, we need to write the mesh equations for these 2, right? So applying KVL for writing mesh equation, we need to have the KVL being applied to mesh 1. Now if we apply KVL to mesh 1, what is the equation here? So it will be given by 8 minus 5I1 minus 4I1 minus I2. That is equals to 0. Right? So if at all I resolve this, I'll be having the equation as 9I1 minus 4I2 is equals to 8. That is the first equation. Right? Once again, applying KVL to mesh 2. To this mesh, if at all I apply the KVL equation, then starting with this 4 ohms. So now 4 is I2 minus I1 plus 6 I2 plus 2 into I2 minus I3. Right? And now in this, I2 is unknown, I1 is unknown, but we know the value of I3. Right? What is the value of I3? I3 is equals to minus 2. So it is minus of minus 2. So this becomes plus 2 here. So I may just keep it as plus 2 is equals to 0. Resolving this particular equation, I'll be having 4I1 minus 12I2 is equals to 4. This is second equation. Right? Solving the 2 simultaneous equations 1 and 2, will be getting I1 as 0.869 amperes and I2 will be negative as 0.0 minus of 0.043 amperes. Right? So now we got all the 3 mesh currents. I1 is 0.869 with the positive direction. I2 is having a negative direction. We have considered it as clockwise, but the actual direction is anti-clockwise with the magnitude of 0.043, and I3 that itself is minus 2 amperes. Fine. If that is so, the question is finally find the current in 4 ohms. So the current in 4 ohms, if at all I just see here, the current in 4 ohms is given by I1 minus I2. Fine. I1 minus I2. I1 is 0.869 minus I2. I2 is minus of 0.043. So that becomes 0.043. So this becomes 0.912 amperes. So the current flowing in 4 ohms becomes 0.912 amperes. Fine. Moving on with the next. Find the current I using nodal analysis in the circuit shown. For the circuit shown here, we need to find the current I. I, the current flowing in this 4 ohms using nodal analysis. Now, once again, for the nodal analysis, we need to know how many are the junctions present in this particular network. So, the number of junctions, and we'll also assign the junction voltages. Fine. So, now for this particular, we are having V1 as the first junction, this as the second junction. These are all at the same potential. So, I'm considering them to be at V3 at 0 potential, right? Now, applying KCL at first junction. KCL at junction 1. Now, at this first junction, if at all I see, I'm having 3 branches, and if at all I consider that V1 is at the highest potential, right? If V1 is at highest potential, all the currents will be flowing outward from this particular junction, say I1 plus I2 plus I3. If at all I apply KCL, I'll be having I1 plus I2 plus I3 is equals to 0. Okay. How can I write I1 as? I1 would be given as V1 by 3. I2 is given as, if we just see here, it is V1 minus 12 upon 6, and I3 is flowing between 1 and 2, so it will be given as V1 minus V2 upon the resistance 2. Any more junction, any more branch? No. So that is equals to 0. So I1 plus I2 plus I3 is equals to 0. Now if it all resolve this, the equation will be getting it as 6V1 minus 3V2 is equals to 12. Right? Similarly, applying KCL at junction 2. When we apply KCL at junction 2, once again, we are having 3 branches, I4, I5 and I6. Although I know that this I4 is equals to minus of I3. I may write it that way as well, right? But this is for simplification, no confusion. This is a different junction, this is a different junction, right? So we are writing it for a different with different name, I4, I5 and I6. Once again, this time I am considering that V2 is at highest potential. If V2 is at highest potential, all the currents will be flowing outward from this particular junction. So we'll be having now I4 plus I5 plus I6 is equals to 0. How can I write I4 this time? Now I4 is flowing from 2 to 1. So I'll be writing it as V2 minus V1 upon 2. Because we are considering this time V2 as higher potential, that's why we have given the direction towards V1, right? So I'll be writing it as V2 minus V1 upon 2 plus I5. I5 at all, once again, if at all I see, this itself is a current source. We need not to write it as some voltage divided by resistance. The current itself we know for this particular branch. And what is the current? That is 4 amperes upward. We are considering it as downwards. So instead of positive, we'll be writing it as negative. So it will be minus 4 plus I6, that is the current flowing in 4 ohms. So I'll be considering it as V2 upon 4. That is equals to 0, right? Once again, resolving this equation, will be having it as minus 2V1 plus 3V2 is equals to 16. This is equation number 2. Now we are having 2 equations. We were having 2 unknowns. V3 is already known to us. Solving these 2, will be having V1 as 7 volts and V2 as 10 volts, right? V1 will be getting it as 7 and V2 as 10 volts. Fine. If that is so, majority of the question has been solved. Now the question is not only knowing the junction voltages. The question is, with these junction voltages, we need to know how much is the current I, that is the current flowing in 4 ohms. So this small I, which is nothing but the current flowing in 4 ohms, would be given by V2 upon 4. V2 is 10. 10 upon 4 is 2.5 amperes downward. So this is going to be the current. Coming with the fourth question, that is, explain the phenomena of resonance in series RLC circuit and also derive the expressions for the cutoff frequency, the bandwidth and quality factor. Fine. So what is the phenomena of resonance in series RLC circuit? So let's once again find out the resonance phenomena using the circuit RLC circuit, right? Now once again, if R, L and C, if they are connected in, this is a variable frequency device although, so connected with an alternating supply voltage with a variable frequency device, the current flowing is I. For a series circuit, we know that these 3 series elements will be having a common current, but the voltages would be divided. The voltage divided would be, say this is, here the resistive voltage would be VR, here it will be VL, here it will be VC, right? Now if at all I represent all these quantities in a phasor diagram. Now what should be the reference phasor? The reference phasor should be the quantity which is common to all the 3, and the quantity which is common to all the 3 is current. So let's have the current as the reference phasor. Where should be VR? VR is the resistive voltage which will be in phase with the current. So VR would be in the same phase. Where should be VL? VL is the inductive voltage. For a purely inductive circuit, the current lags the voltage, right? So if the current lags the voltage, that means the voltage leads. The voltage leads. VC, where should be VC? For a purely capacitive circuit, the current leads. That means the voltage will lag. This is the phasor diagram. Now we are saying for resonance, one thing is there that for any resonance, let that be a series or parallel resonance, one of the characteristic is the circuit's power factor is going to be unity. And for making this circuit power factor unity, what should be the condition? That can be seen from the phasor diagram. From the phasor diagram, it is very much clear that for having power factor unity, the total supply voltage and the current should be in same phase. And that is only possible when VL and VC are going to remain same. That means the voltage across capacitor and the voltage across the inductor, both are going to remain same. They are in antiphase, will cancel out each other, and will be remaining with just VR, which is in phase with current, and this will be nothing but the supply voltage at resonance state, right? So this is the phasor diagram as well as the phenomena of resonance in series RLC circuit. So if at all I see what are the characteristics of this series resonance circuit. So we come to know that first the thing is the power factor has to be unity. With that, if the power factor is unity, for this, making this power factor unity, what is the condition? We come to know that for making this, VL should be equals to VC, or I may be saying VL is given by I into XL, VC is given by I into SC, but I is same in both the circuit. It means what? That XL must be equals to XC, right? That the inductive reactance must be equals to the capacitive reactance offered by the inductor and capacitor. That should be same. Fine. The third, if both of these are going to remain same, what will be the total impedance offered to the circuit? As we know, for a series resonant circuit, the impedance offered is actually R square plus XL minus XC whole square. But at resonance, these two are same. If these two are same, the resistance, the impedance offered by the circuit is going to be only R, and this is going to be the minimum value, right? So this is going to be the minimum value. So at resonance, the impedance would be, first of all, minimum and its value would be equals to R. Okay. If the impedance is minimum, what is going to be the current at resonance? If the impedance is minimum, the current is going to be maximum, and that is given by V upon Z, but Z is equals to R. So the current is also going to remain maximum. If the current is maximum, the power will also be maximum. Right? Now, all these phenomena, if at all I see, is occurring with respect to frequency. What we are changing actually? What we are changing? When XL is becoming equal to XC, this is happening at certain frequency, because XL and XC are frequency dependent devices. Resistance is not frequency dependent. It is going to remain same, right? So at that particular frequency at which the inductive reactance is becoming equals to capacitive reactance, at that frequency this resonance is going to occur, and that frequency is being called as resonant frequency, and that is given by 1 upon 2 pi under root LC. So these are certain characteristics for a series resonant circuit. So we have discussed the phenomena and what are the characteristics for a series resonant circuit. Now we need to derive the expressions for the cutoff frequency, for the bandwidth, and for the quality factor. Now, so starting with, now if at all I say for the series circuit, how can I give for a normal RLC series circuit? How can I give the expression for the current? The current is given by V upon Z, okay, and Z is given by under root of R square plus XL minus XC whole square, right? Or I may write it as V upon under root R square plus XL, I may write it as omega L minus 1 upon omega C whole square. This is first equation I may be writing, fine. But at half power points, at cutoff frequencies, right, at half power points where the maximum power is being halved, at that instant, the current becomes maximum by root 2 value, right? The current is maximum current by root 2. At that instant, I may be writing current is equals to, the current is becoming root 2. Im by root 2, right? And Im by root 2 can be written as Im is V upon R, this is root 2, right? So these two I may be just equating 1 and 2. Just equating the two equations, this is equals to V upon root 2 R. If that is so, I may be having R square plus omega L upon 1 upon omega C square under root is equals to root 2 R. Right? Squaring both the sides, removing R square terms, will be having omega L minus 1 upon omega C is equals to plus or minus R. Right? Once again, because we need to have the two cutoff frequencies and we need to solve this, so what we can do is, we can assign, it is plus minus R because it was under root. So I may be just considering that omega 2L minus 1 upon omega 2C is equals to some positive R, and omega 1L minus 1 upon omega 1C is equals to some minus R, right? When we add these two equations, we'll be coming to know that omega R is equals to under root of omega 1, omega 2. So that means it is the geometric mean of the two cut-off frequencies omega 1 and omega 2, or I may be saying FR is equals to under root F1 and F2. When we subtract these two equations, right, this is equation number 3 and 4. If at all I subtract equation number 3 and 4, we are going to have omega 2 minus omega 1 is equals to R by L, right? Omega 2 is corresponding to the upper cutoff frequency and F2, and omega 1 is corresponding to the lower cutoff frequency F1, that will be given by R upon 2 pi L, where this F2 minus F1 is actually nothing but the bandwidth, right? what are the two if bandwidth? If at all I go with the power graph, if this is the maximum power which is occurring, we just see at resonant frequency, right? At the half power points where the maximum power is being halved, will be having the two cutoff frequencies, F1 and F2. And the frequency and the difference of these two cutoff frequency is given by the bandwidth. That means F2 minus F1 gives the bandwidth. The instant at which the maximum power is being halved is the one where the maximum current becomes upon root 2, right? So, the bandwidth is given by R upon 2 pi L in terms of circuit constants, right? Now, if this is so, I may be just saying that, obviously, we in the earlier case also we derived that FR is the geometric mean of the two, right? So, I may just consider that this is certain delta F and this is also certain delta F, right? It is lying at the center. If that is so, I may be writing that this bandwidth is actually equals to twice of delta F, which is R upon 2 pi L. It means delta F is equals to R upon 4 pi L, right? If that is so, now I may be giving F1 is equals to FR minus delta F, where delta F is R upon 4 pi L, and F2 can be given as FR plus delta F, right? So, we have derived the expression for bandwidth, for the lower cutoff frequency, for the upper cutoff frequency, and finally, the quality factor. Now, the quality factor for a series resonant circuit, it is given by the voltage magnification which is occurring in the circuit at resonance, right? So, if we just see in case of series resonant circuit, right, at the resonant state, the voltage across the inductor and capacitor are going to be maximized, they are going to be magnified many times compared to the supply voltage. But both of these are in antiphase, so they are going to cancel out each other. They are in antiphase, but the magnitude of the voltages across inductor and capacitor, they are many folds greater than the supply voltage, right, as the current becomes maximum. So, the voltage magnification which is occurring either the inductor or the capacitor, because both the voltages are same, right, that is defining the quality factor for a series resonant circuit, right. So, the quality factor is given by the voltage magnification occurring across inductor, or that means it can be given as VL or VC upon the supply voltage or the resistive voltage, because at resonance the supply voltage is equals to the resistive voltage. Once again, if at all I go with VL upon V, VL can be given as, at the resonance the current is IM into XL by V. Once again, IM, that is the maximum current, multiplied by XL. XL is the inductive reactance at resonance, given by omega L, omega RL resonance, right, by V. Once again, IM, that is the maximum current, given by V by R. So, this becomes omega RL by R. So, the quality factor is given by omega RL by R. If at all we just see here, I may write it as omega R by L, where what is R by L? That is bandwidth. So, I may write it as omega R by bandwidth as well. So, that is the relationship between quality factor and bandwidth. In fact, if at all I substitute, I know that the value of omega R is under root LC, right? This is the resonant frequency in radians per second. So, if that is so, I substitute omega R as under root L by C. I will be having the quality factor as 1 upon R under root L by C. So, we may be giving quality factor in the terms of circuit constants as 1 upon R under root L by C. It is inversely proportional to the bandwidth and directly proportional to the resonant frequency omega R. going with the next question of the question 4th, that is, a three-phase voltage source has a phase voltage of 120 volts and supplies a star-connected load having impedance of 36.J48 ohms per phase. Calculate the line voltage, the line current, the power factor, the total three-phase power supplied to the load. Now, the things which are given to us, what are the things given to us is, we know that the phase voltage which is given to us is 120 volts, right? We are having a star connected load, right? That means the impedance per phase becomes 36 plus J48 ohms, right? If at all I convert it into polar form, because we need to go for the division and the division is easier in case of polar. So converting 36 plus J48 into polar form, I'll be getting it as 60 angle 53.13 ohms. So this becomes the impedance per phase. Now to calculate, first the thing we need to know is the line voltage, right? For a star connected system, the line voltage is equals to √3 times the phase voltage, right? So √3 times the phase voltage, that means √3 to 120. So the voltage becomes 207.84 volts. So this is our line voltage. Fine. Now the line current. For a star connected system, the line current is equals to the phase current, right? And directly, in fact, for any numerical, we can't directly go for the line voltage. We have to find first of all the phase current, right? For finding phase current, we know it has to be V phase by Z phase. The same can't be applied to the line values. I can't find IL is equals to VL by ZL because there is no line value for impedance. The impedance, let it be star connected, let it be delta connected, the impedance is always having a phase value. So the relationship exists only for the phase values, not for the line values. So in any of the case, we are going to first find out how much is the I phase, the phase current. So that is given by V phase by Z phase. V phase is 120 with an angle of 0. So, and now the impedance is 60 with an angle of 53.13. So this gives me 2 with an angle of minus 53.13 amperes. Now is given the power factor. The power factor is given by R by Z, or directly I may be just finding it off with cos phi, where phi is the angle between voltage and current, which is given by the impedance itself. When we find the impedance, whatever is the angle of impedance, that is nothing going to be the phi. So cos of 53.13 gives us 0.6. Whether it is leading or lagging, it itself is 36 plus J48. It means it has to be lagging. The current what we are getting, it is with a minus sign. So it is lagging. Now finally, the total power taken. The total power taken is 3 VPH IPH cos phi, right? So 3 VPH is 120, IPH is 2, what we came to know, and multiply the power factor, what we got it as 0.6. So the power becomes 432 watts. So thank you all. We'll be continuing the same with the remaining sections with the remaining questions. Thank you.